Tonight we are going to explore one of the most profound discoveries in the history of astronomy. Something so unexpected, so fundamentally challenging to everything we thought we understood about the universe, that when astronomers first saw the data they questioned whether their instruments were working correctly. The James Webb Space Telescope has peered deeper into space and further back in time than any instrument in human history. And what it found at the edge of observable reality should not exist. These discoveries are not just surprising, they are impossible according to our best theories of how the universe works. When you look up at the night sky and see stars scattered across the darkness, you are looking back in time. Light travels at a finite speed about 300,000 kilometers per second. When you see a star 10 light years away, you are seeing light that left that star 10 years ago. You are seeing the star as it was in the past, not as it is now. This means that the farther out into space we look, the further back in time we are seeing. Distant galaxies show us what the universe looked like billions of years ago, when those galaxies were young, and the cosmos itself was in its infancy. The James Webb Space Telescope was designed specifically to look at these most distant objects, to peer back to the very beginning of cosmic history and witness the birth of the first galaxies. Astronomers had clear predictions about what they would find. The early universe should have been relatively simple. The first galaxies should have been small, irregular, chaotic collections of stars slowly assembling over hundreds of millions of years. They should have been faint, primitive, nothing like the massive, well-organized galaxies we see in the local universe today. But when Webb turned its powerful infrared eyes toward the deepest reaches of space, it saw something completely different. It saw galaxies that were massive, mature, and organized, existing at times when they simply should not have been able to form. It saw galaxies producing stars at rates that violate our understanding of physics. It saw galaxies that had already died, that had stopped forming stars entirely, at epochs when the universe was supposed to be a cosmic nursery overflowing with the raw materials for star birth. These discoveries have sent shockwaves through the astronomical community. Some scientists are calling it a crisis in cosmology. Others are more measured, suggesting that we simply need to revise our models. But everyone agrees that what Webb has found is profoundly strange and deeply challenging. So what exactly did James Webb see? What are these impossible objects lurking at the edge of reality? And what do they mean for our understanding of the universe, its history, and the laws that govern it? Tonight we are going to explore these questions in depth. We are going to look at the specific discoveries that have astronomers so concerned. We are going to understand why these objects should not exist according to standard cosmology. And we are going to consider what explanations might resolve these mysteries, or what fundamental revisions to physics might be required. The story begins with distance. To understand what Webb has found, we first need to understand how astronomers measure vast cosmic distances and peer back billions of years in time. The key is something called redshift. When light travels through expanding space, the wavelengths of that light get stretched. Light that was emitted as blue or ultraviolet can be stretched so much that by the time it reaches us, it appears as red or even infrared light. This stretching is caused by the expansion of the universe itself. Space is growing larger, and as it does, light traveling through that space gets stretched along with it. The amount of stretching tells us how far away an object is and how long ago the light was emitted. Astronomers use a number called Z to describe redshift. A redshift of Z equals 1 means the wavelengths have been stretched by a factor of 2, doubling in length. A redshift of Z equals 2 means they have been stretched by a factor of 3, tripling, and so on. Higher redshift means greater distance and earlier time. Objects with redshifts above Z equals 6 are seeing us, as the universe was less than 1 billion years after the Big Bang. Objects above Z equals 10 are seeing us, as the universe was less than 500 million years old. And Webb has been finding objects at redshifts of 14 and higher, showing us the universe when it was only 2 to 300 million years old, barely 2% of its current age. At these extreme distances and early times, everything we observe challenges our expectations. The universe at 300 million years old should have been a very different place from what we see today. Stars were just beginning to form. Galaxies were in their earliest stages of assembly. The cosmos was emerging from what astronomers call the Dark Ages, a period after the Big Bang when the universe had cooled enough for atoms to form, but before the first stars ignited and began lighting up the darkness. According to standard cosmological models, the first galaxies should have been small. Gravity would have pulled together clumps of dark matter and gas, and within those clumps, the first stars would ignite. These proto-galaxies would be tiny, perhaps containing only a few million stars, nothing like the hundreds of billions of stars in a mature galaxy like the Milky Way. Over time, these small galaxies would collide and merge, slowly building up into larger structures. This process should take hundreds of millions or even billions of years. The massive, well-formed galaxies we see in the nearby universe should not appear until the cosmos is much older. But Webb has found massive galaxies at redshifts above 14. One of the most dramatic examples is a galaxy called JWST GSZ 14-0. This object holds the current record for the most distant galaxy ever confirmed with spectroscopy. It exists at a redshift of about 14.32, corresponding to just under 300 million years after the Big Bang. When astronomers measured the spectrum of this galaxy to confirm its distance, they found something astonishing. The galaxy is huge and incredibly luminous. It spans more than 1,600 light-years across and shines with the light of hundreds of millions of stars. This should not be possible. At 300 million years after the Big Bang, there simply has not been enough time for gravity to assemble this much mass into a single coherent structure. Think of it this way. Gravity works slowly. It takes time for matter to clump together under its own weight, for gas clouds to collapse, for stars to form. In the early universe, matter was spread relatively evenly throughout space with only tiny variations in density. These small overdense regions would gradually attract more matter, growing denser and denser until eventually stars could form. But this is a gradual process. It should not produce massive, mature galaxies in just a few hundred million years. To make the situation even more puzzling, JWST GSZ 14-0 is not just massive and bright. Its spectrum shows strong emission lines from hydrogen and oxygen. Oxygen is a heavy element produced inside stars through nuclear fusion. When massive stars explode as supernovae, they scatter this oxygen into space, enriching the surrounding gas with heavy elements. The presence of oxygen in JWST GSZ 14-0 means that multiple generations of stars must have already lived and died in this galaxy. Stars had to form, fuse lighter elements into heavier ones over millions of years, explode, enrich the interstellar medium, and then new stars had to form from that enriched gas. All of this had to happen in less than 300 million years. It is like arriving at a construction site on the first day and finding a completed skyscraper already standing there. The timeline does not add up. And JWST GSZ 14-0 is not alone. Webb has discovered another extremely distant galaxy called JWST GSZ 14-1, also at a redshift around 14. Together, these objects and others like them form a population of early galaxies that are far more luminous and massive than any theoretical model predicted. Astronomers have nicknamed some of these objects universe breakers because they seem to break the standard cosmological model. The discovery paper describing JWST GSZ 14-0 and its companion was published by an international team led by researchers including Brant Robertson at the University of California, Santa Cruz and Stefano Carniani in Italy. When they announced the findings in 2024, Robertson called it completely unanticipated and likely to be seen as the most significant extragalactic discovery with Webb to date. The team emphasized that these galaxies do not match the types of galaxies predicted by theoretical models and computer simulations for the very early universe. Something is wrong with our understanding. Either the galaxies are not what they appear to be, or the physical processes in the early universe worked very differently from what we have assumed. What makes JWST GSZ14-0 especially interesting is its size and the source of its light. Many very luminous objects in the distant universe are powered not by stars, but by supermassive black holes. When matter falls into a black hole, it forms a swirling disk of gas that heats up to millions of degrees and emits intense radiation. This creates what astronomers call an active galactic nucleus, or AGN, often visible as a quasar. Quasars can be far brighter than all the stars in a galaxy combined, so a small galaxy with an actively feeding black hole can appear very luminous. Initially, some astronomers wondered whether JWST GSZ14-0 might be a quasar rather than a normal star-forming galaxy. If the light were coming mostly from a black hole rather than from stars, it would be less surprising to find such a bright object so early. Black holes can form relatively quickly compared to the slow assembly of stellar populations. However, the observations ruled this out. The galaxy is too large and too extended for its light to be coming from a central point source like a black hole. The light is spread across 1,600 light-years of space, clearly indicating that it is produced by a large population of young stars distributed throughout the galaxy. This is not a quasar. It is a genuine massive star-forming galaxy existing impossibly early in cosmic history. Even more perplexing, the galaxy shows signs of dust. Dust in astronomy refers to tiny solid particles made of heavy elements like carbon, silicon, and iron. Dust forms in the atmospheres of dying stars and in supernova explosions. The presence of dust means that not only have multiple generations of stars lived and died, but enough time has passed for that stellar material to condense into solid grains. In the local universe, dust is common. It obscures visible light and makes distant galaxies appear redder than they would otherwise. But in the very early universe, there should not be much dust yet because not enough stars have lived and died to produce it. Yet JWST GSZ14-0 shows clear evidence of dust reddening, another sign that this galaxy has matured far faster than it should have. The team also detected the galaxy using Webb's mid-infrared instrument, or MIRI. This is remarkable because MIRI observes at longer wavelengths than the near-infrared cameras, and detecting such a distant object in the mid-infrared indicates that the galaxy is even brighter than initially thought. The MIRI detection suggests strong ionized gas emission from the galaxy, meaning there are regions of intense star formation where hot young stars are ionizing the surrounding hydrogen and oxygen. All of these details paint a picture of a galaxy that is actively, vigorously forming stars, and has already undergone substantial evolution despite existing only 300 million years after the universe began. But the surprises do not stop there. In November 2024, another team announced the discovery of 3 more massive galaxies in the early universe that challenge our understanding even further. These 3 objects, dubbed the Red Monsters, were discovered using spectroscopic data from Webb's first reionization Epoch Spectroscopic Complete Observations Survey, known as FRESCO. The Red Monsters exist within the first billion years after the Big Bang and have stellar masses comparable to the Milky Way galaxy. Each one contains about 100 billion times the mass of the Sun in stars. What makes the Red Monsters so shocking is not just their size but their efficiency at forming stars. According to standard theory, when galaxies form, only about 20% of the available gas gets converted into stars. The rest is heated by various processes, blown away by stellar winds and supernovae, or simply fails to collapse under gravity. This low efficiency is built into our models based on observations of galaxies throughout cosmic history. Stars form slowly and inefficiently, That is the norm. But the red monsters appear to have converted nearly 80% of their gas into stars. That is 4 times more efficient than any galaxy should be. They are forming stars at roughly twice the rate of lower-mass galaxies at the same epoch and galaxies at later times. This is completely unexpected. Star formation is supposed to be a messy, inefficient process. There are many mechanisms that prevent gas from collapsing into stars. Radiation pressure from existing stars pushes gas away. Supernovae explosions heat and disperse gas clouds. Turbulence and magnetic fields can prevent gravitational collapse. For a galaxy to convert 80% of its gas into stars means all these regulatory processes somehow failed to operate or were overcome by some unknown mechanism. The red monsters get their name from their appearance in Webb images. Due to their high dust content, they appear distinctly red. Dust absorbs shorter wavelength blue and ultraviolet light and irradiates it at longer infrared wavelengths, making dust-rich objects appear red in infrared imaging. Before Webb, these objects were essentially invisible because optical telescopes like Hubble could not see through the dust. Webb's infrared vision allows it to peer through the dust and reveal these hidden giants. The Discovery team, led by Menju Zhao at the University of Geneva, published their findings in the journal Nature in November 2024. In their paper, they emphasized that while most galaxies observed in the FRESCO survey fit existing models reasonably well, these 3 ultramassive galaxies stand out as clear anomalies. Zhao stated that their findings are reshaping our understanding of galaxy formation in the early universe. The team includes researchers from institutions around the world, including Pieter van Dokkum at Yale University, who compared discovering the red monsters to coming home expecting to find a kitten and instead finding a cougar on your couch. It is that level of unexpected. David Elbaz, one of the co-authors from CEA Paris-Saclay, noted that the massive properties of the red monsters were hardly determined before Webb because they are optically invisible due to dust. Only with Webb's infrared capabilities could these objects be studied in detail. And what that detailed study revealed is that star formation in the early universe could proceed with unexpected efficiency under certain conditions. But what conditions? That is the mystery. Why would some early galaxies form stars so efficiently while others follow the standard inefficient process? One possibility is that these galaxies had access to unusually large amounts of cold, dense gas, the raw material for star formation. Another possibility is that the gas in these galaxies cooled more quickly than usual, allowing it to collapse under gravity before heating and feedback processes could disrupt it. Or perhaps there is some aspect of the early universe, some property of the gas or the dark matter halos that contained it, that we do not yet understand. The red monsters challenge our models, but they do not necessarily overturn them. The standard cosmological model, based on general relativity and the Big Bang theory, is incredibly well tested. It explains a vast range of observations, from the cosmic microwave background radiation to the large-scale structure of galaxies to the abundances of light elements formed in the first few minutes after the Big Bang. Scientists are not ready to abandon that framework. Instead, they are exploring how modifications or additions to galaxy formation theory might explain these anomalous objects. Perhaps star formation in the very early universe, when matter was denser and conditions were more extreme, operated by different rules than it does later. Perhaps these red monsters represent a rare but natural outcome of standard physics in an unusual environment. Or perhaps there is genuinely new physics at play, something we have not accounted for. And then there is another class of impossible objects that Webb has discovered, galaxies that are not just massive and mature too early, but galaxies that are already dead. Galaxies stop forming stars when they run out of gas. In the local universe, we see plenty of dead galaxies. These are typically massive elliptical galaxies that have used up or lost their gas and now contain only aging stars with no new star formation. The processes that shut down star formation are complex. They can include feedback from supermassive black holes, which heat and eject gas from the galaxy. They can include mergers with other galaxies, which can trigger bursts of star formation that quickly exhaust the gas supply. They can include simply running out of fresh gas as the galaxy ages, and the cosmic web delivers less and less new material. But all of these processes take time. A galaxy needs to form, accumulate gas, form stars, and then exhaust or lose that gas. This should not happen quickly. In the early universe, when gas was plentiful and the cosmic buffet was wide open, galaxies should have been actively forming stars. Finding a dead galaxy in the early universe would be surprising. Finding one that died only 700 million years after the Big Bang should be impossible. Yet in March 2024, astronomers announced the discovery of exactly that. Using data from the JWST Advanced Deep Extragalactic Survey, or JADES, a team led by Tobias Lusser at the University of Cambridge identified a galaxy called JADES GSZ701QU. This galaxy exists at a redshift of about 7.3, corresponding to about 700 million years after the Big Bang, and it is completely dead. It has stopped forming stars. The discovery was published in the journal Nature and immediately sparked intense discussion. JADES GSZ701QU is the oldest known quenched galaxy, the oldest example of a galaxy that has shut down star formation. According to the data, this galaxy experienced a short but intense burst of star formation lasting between 30 and 90 million years. During this period, it formed a substantial population of stars. Then, about 10 to 20 million years before the epoch at which Webb observed it, star formation suddenly stopped. The galaxy went dark. No new stars have formed since. This is profoundly strange. The early universe was full of gas. Galaxies at this epoch should have been voraciously consuming gas and forming stars. As Lusser put it in interviews, the first few hundred million years of the universe was a very active phase with lots of gas clouds collapsing to form new stars. Galaxies need a rich supply of gas to form new stars, and the early universe was like an all-you-can-eat buffet. So why did this particular galaxy suddenly stop eating? Why did it shut down star formation when it should have been in the prime of its life? There are several mechanisms that can quench star formation in galaxies, but none of them seem to fit JADES GSZ701QU. One possibility is feedback from a supermassive black hole. If the galaxy harbored an actively feeding black hole, the energy output from matter falling into the black hole could heat the surrounding gas and prevent it from collapsing into stars. This process, called AGN feedback, is known to shut down star formation in massive galaxies in the local universe. However, the team found no clear evidence of an active galactic nucleus in JADES GSZ701QU. The galaxy does not show the spectroscopic signatures expected from a feeding black hole. Another possibility is that the burst of star formation itself shut the galaxy down. When many massive stars form in a short period, they produce powerful winds and eventually explode as supernovae. This stellar feedback can heat and expel gas from the galaxy, temporarily halting star formation. But this process usually creates a temporary lull, not a permanent shutdown. Galaxies affected by stellar feedback typically resume forming stars once the feedback subsides and new gas accretes onto the galaxy. JADES GSZ701QU appears to have stopped forming stars permanently, or at least for a substantial period of time. A third possibility is that the galaxy simply consumed or lost all its gas very quickly. Perhaps the initial burst of star formation was so intense that it used up the gas supply faster than new gas could be delivered from the cosmic web. This would be unusual because the early universe had so much gas available. Galaxies at this epoch should have been continually fed with fresh gas from the surrounding intergalactic medium. But perhaps JADES GSZ701QU was in an unusual environment, maybe an underdense region where gas was scarce, leading to its early demise. Roberto Maialino, another co-author of the study, emphasized that current models based on the modern universe struggle to explain JWST Z701QU. Until now, astronomers have used models of galaxy formation developed from observations of nearby galaxies and extrapolated those models back to the early universe. But now that Webb can actually observe the early universe directly, it is becoming clear that those extrapolations may not be valid. The early universe might have operated differently. Galaxies might have formed and evolved in ways that do not match what we see today. As Maialino put it, models based on the modern universe may need to be revisited. There is also the tantalizing possibility that JWST Z701QU is not permanently dead. Perhaps it will come back to life. Some theoretical models suggest that galaxies in the early universe might experience cycles of star formation, turning on and off as gas is consumed and replenished. In this scenario, JWST Z701QU might be in a temporary quenched state and will resume forming stars later. However, studies of dead galaxies at later epochs suggest that once a galaxy shuts down, it typically stays shut down. Even mergers with other galaxies do not reliably restart star formation in quenched galaxies. They tend to just make the dead galaxy larger without rekindling star birth. The discovery of JWST Z701QU is particularly important because it is also relatively low mass. It has a stellar mass similar to the Small Magellanic Cloud, a small dwarf galaxy orbiting the Milky Way. The Small Magellanic Cloud is still forming stars actively today, but JWST Z701QU, with a similar mass, has already gone dark at a time when the universe was barely 5% of its current age. Previously discovered dead galaxies in the early universe have been much more massive. The fact that even small galaxies could shut down so early is another puzzle. It suggests that whatever process quenched JWST Z701QU was powerful enough to affect even low-mass systems. All of these discoveries, from JWST Z140 to the red monsters to JWST Z701QU, point to the same conclusion. The early universe was far more complex and dynamic than our models predicted. Galaxies were forming faster, growing larger, producing stars more efficiently, and shutting down sooner than we thought possible. The neat, orderly picture of gradual galaxy assembly over billions of years is being challenged by observations of rapid, chaotic, highly efficient processes in the first few 100 million years of cosmic history. So what do these discoveries mean for cosmology? Are they truly universe breakers? Do they require us to abandon our models and start from scratch? Or can we modify existing theories to accommodate these new observations? The answer depends on who you ask and how optimistic they are about finding solutions within the current framework. Some astronomers argue that these discoveries represent a genuine crisis. They point out that the standard model of galaxy formation, based on cold dark matter and hierarchical assembly, makes specific predictions about the number and properties of galaxies at high redshift. And those predictions are now clearly wrong. There are too many massive galaxies too early. There are too many dead galaxies too early. The observed star formation efficiency is too high. Something fundamental is missing from our theories. Others are more cautious. They argue that galaxy formation is incredibly complex and that our models have always been approximations. The detailed physics of how gas cools, how stars form, how feedback operates, these processes are not fully understood even in the local universe. Extrapolating them to the early universe introduces significant uncertainties. Perhaps with more sophisticated simulations and a better understanding of the physical processes involved, we can explain the Webb observations without changing the fundamental cosmological framework. The Big Bang Theory, dark matter, dark energy, these pillars of modern cosmology remain secure. What needs revision is our understanding of how baryonic matter, the ordinary stuff of stars and gas, behaves in the extreme conditions of the early universe. There is also the possibility that some of the observed galaxies are not what they appear to be. Astronomers have raised the possibility that some of the bright compact sources in the early universe, sometimes called little red dots, might be powered by black holes rather than stars despite their extended appearance. If a supermassive black hole is surrounded by a compact but spatially extended region of ionized gas, it might mimic the appearance of a star-forming galaxy. This would make the object appear less massive than inferred, because the mass would be dominated by the black hole rather than by stars. However, for many of the discovered galaxies, including JWST Z14-0 and the red monsters, the evidence strongly favors a stellar origin for the light. These really are massive populations of stars, not hidden quasars. Another intriguing possibility is that star formation in the early universe involved a different initial mass function, or IMF. The IMF describes the distribution of stellar masses when stars form. In the local universe, most stars that form are low-mass stars like red dwarfs, with fewer intermediate-mass stars and even fewer massive stars. But some theoretical models suggest that in the early universe, when the gas was more pristine and metal-poor, star formation might have favored more massive stars. If the first generations of stars were predominantly massive, they would have been much brighter and would have produced heavy elements much faster through rapid supernova explosions. This could explain both the high luminosity of early galaxies and the presence of heavy elements like oxygen so early in cosmic history. However, this idea remains speculative and does not fully resolve all the tensions. What is clear is that the James Webb Space Telescope is fundamentally changing our view of the early universe. Before Webb, our knowledge of galaxies at redshifts above 10 was extremely limited. Hubble's Space Telescope could barely detect objects at these distances, and spectroscopic confirmation was nearly impossible. Astronomers relied on theoretical models and simulations to predict what the early universe should look like. Webb has now provided the observational data to test those models. And the models are failing the test. This is actually an exciting time for cosmology. When observations challenge theory, science advances. The discoveries Webb is making will drive new theoretical work, new simulations, and new physical insights. Over the coming years, astronomers will continue to study these early galaxies in greater detail. Webb will obtain deeper spectroscopy to measure the physical conditions in these galaxies more precisely. It will search for more examples of massive, dead, and anomalous galaxies to determine how common these objects are. And other observatories, like the Atacama Large Millimeter Array in Chile, will complement Webb's observations by studying the cold gas and dust in these systems. One key question is whether the red monsters and other ultramassive galaxies represent a common phase of galaxy evolution, or whether they are rare outliers. If they are common, if many early galaxies achieved near-complete gas-to-star conversion efficiency, then our models need a major overhaul. But if they are rare, if only a small fraction of galaxies behave this way, then perhaps standard models can accommodate them as statistical flukes or the result of unusual environmental conditions. The answer will come from larger surveys that can determine the number density of these objects. Another important question is whether the dead galaxy JWST Z701QU is unique or the tip of an iceberg. If quenched galaxies are common at high redshift, it would imply that star formation shutdowns can happen rapidly and frequently in the early universe. If JWST Z701QU is a rare anomaly, it might simply be an interesting curiosity. Webb's deep surveys will reveal more dead galaxies if they exist, and their properties will constrain the mechanisms that shut down star formation. There is also the intriguing possibility that these observations hint at new physics beyond the standard model. Dark matter, which makes up most of the mass in galaxies and the universe, is still poorly understood. We know it exists because of its gravitational effects, but we do not know what it is made of. Most models assume that dark matter is cold, meaning it moves slowly and clumps into halos efficiently. But if dark matter has different properties, if it interacts with itself or with ordinary matter in subtle ways, it could affect how galaxies form. Some alternative dark matter models predict that halos in the early universe could collapse faster or be denser than standard cold dark matter predicts. This could accelerate galaxy formation and lead to the massive early galaxies Webb has discovered. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, is assumed to have constant properties over cosmic time. But what if dark energy evolves? What if it was stronger or weaker in the early universe? Changes in dark energy would affect the expansion rate and the growth of cosmic structure, potentially altering the timeline of galaxy formation. However, these ideas remain highly speculative. The evidence for standard cold dark matter and a cosmological constant remains strong, and most physicists are reluctant to abandon these ideas without compelling reason. What cannot be denied is that Webb has delivered on its promise to revolutionize our understanding of the early universe. The telescope was conceived decades ago with the explicit goal of observing the first galaxies and stars. Engineers and scientists worked for more than 20 years to design, build, and launch this extraordinary machine. And now, in its first few years of operation, it has already uncovered profound mysteries that will keep astronomers busy for years to come. Garth Illingworth, an emeritus professor at the University of California, Santa Cruz, and one of the scientists who helped initiate the concept that became Webb back in the 1980s, has said that for 3 decades they knew Webb would provide insights into how the earliest galaxies formed and grew. But even he admits that these remarkable results demonstrate that the earliest galaxies are even more unusual and remarkable than anyone ever expected. The universe has surprised us again, and that surprise is the lifeblood of science. So as we close this exploration, let us reflect on what we have learned. The James Webb Space Telescope has found massive galaxies at distances where they should not exist. It has found galaxies forming stars with impossible efficiency. It has found dead galaxies at times when galaxies should be bursting with life. These discoveries challenge our models, push the boundaries of our understanding, and remind us that the universe is far stranger and more complex than we often assume. The edge of observable reality, the most distant reaches of space and time, is not the simple realm we predicted. It is a frontier full of mysteries, anomalies, and wonders waiting to be understood. In the coming years, astronomers will work tirelessly to explain these observations. They will refine their models, run new simulations, and search for new physical mechanisms that can account for what Webb has seen. Some mysteries will be resolved. Others may lead to genuine revisions of our cosmological framework, and still others might point toward entirely new physics waiting to be discovered. This is the scientific process in action: observation, surprise, questioning, theorizing, testing. It is messy and uncertain, and endlessly fascinating. And for us, observing from the sidelines, watching as astronomers unravel these cosmic mysteries, it is a privilege. We live in an era when humanity can peer back to the dawn of time, when we can see the first light from the first galaxies, when we can test our theories of the universe's origin against direct observations. The universe has not run out of mysteries to reveal. And the James Webb Space Telescope, with its unparalleled vision, is showing us that the edge of reality is far more mysterious and wonderful than we ever imagined. If you have enjoyed this deep exploration of the impossible galaxies discovered by Webb, consider leaving a like and subscribing to the channel. These in-depth looks at the cutting edge of astronomy take considerable time to research and create, and your support makes them possible. Share this with anyone who loves space, science, and the mysteries of the cosmos. And keep looking up, keep asking questions, and keep marveling at the universe. Because out there, at the very edge of what we can see, the universe is waiting to teach us something profound. Good night, and may you never look at the night sky the same way again.